Hello, everyone. Thank you for joining today's Slang virtual meetup. In today's session, we will discover Slang's modern module system and how it can revolutionize your shader development workflow. Our speaker today is Yong, Principal Software Engineer at NVIDIA Research. But first, a couple of housekeeping items. If you have any questions during the presentation, please ask using the Q&A feature located on your Zoom toolbar at the bottom of your screen. We are recording this webinar, and we'll post a link to the recording on the Slang website. At the end of the session, please complete the short survey to help us better design future events. With that, I'll hand it off to Yong, Principal Software Engineer at NVIDIA Research. Yong?
Thank you. Let me share my screen for this. Can you see the slides? Is that sharing right now?
Yes, looks great.
Okay. Great. So I will get started. So today I will be talking about Slang modules and how you can use modules to speed up shader compiles. And after that, we'll cover how you can do shader specialization in Slang in a way that allows you to maximize the benefits of using modules. So let's get into that now. So first of all, why modules? It is a cleaner way to organize your code, allowing you to define boundaries between different parts of your software and hide implementation details within a component. And the more attractive benefit is that modules can speed up compilation time. But to get that benefit, you will need to use modules along with several other Slang features to do shader specialization. And that is what I will cover in the second part of this talk. But first, let's talk about how you can use modules in Slang. And here's an example code showing how a module is defined in Slang. In this code, we define a module called materials. And by writing this module materials line, we are just stating that this file is part of the materials module. And we can use visibility modifiers similar to other languages. So here, public means that the type of function can be used from another module. And internal means that the declaration can only be accessed from within the same module. So that would be like implementation detail that's hidden within the module. And a module can also be defined in more than one file. So here, our materials module is defined by 4 files. This materials.slang module, materials.slang file that serves as the main file for this module, and standard.slang, distinct.slang, and skin.slang that all implement different types of materials and included by this main module file. So here, for the main module file, it starts with the module declaration like you see before. And following that, we use a bunch of additional lines to include those additional files into this module. Note that this is not to be confused with the preprocessor pound include. And the main difference is that this underscore include is resolved during type checking and not during preprocessing. And all these included files will start like standard.slang, will start with an implementing declaration to state that this file is part of a module. And you may wonder why the Slang require both include and implementing declarations. And that is because, like on surface, like if you have include, then implementing seems redundant. And the reason for like requiring this implementing declaration is that this is to make it very clear that the file is belonging to some specific module. And it also enables IntelliSense to automatically discover all other declarations in the same module when you edit this file. So for example, here the IntelliSense will be able to highlight this iMaterial type in standard.slang, even though that iMaterial type is not defined in this file. And one thing to note is that within the module, everything is visible to each other. So regardless of which file they are defining. So for example, a function that in standard.slang will be able to call another function defined in skin.slang, for example. simply because they're just both part of the materials module, even though in the standard.slang, I'm not directly including the skin.slang file. And an analogy to a Slang module is it's like a C# or C++ project that compiles into its own static or dynamic library. And the boundary of your library is defined by the public types and methods. And every file within the module can access things defined in a different file. And with the module implemented in one or many files, you can compile it into Slang.ir by running slangc on the main module file. So that's the file with the module declaration. So in this example, it's the material.slang file. And the compiler will perform type checks on the source code and then produce this materials.slang module binary file. And this binary file contains two things. The AST nodes that define the signatures of the types and functions, and the function code represented in the Slang.ir. Note that regardless how many .slang files are used to define this materials module, the compile module is always just one materials.shader .slang module file. So that's how you will write and compile a module. So let's see how you can use that module. You can use the module by simply importing it like many other languages. So here we define another module called compute, and that defines a compute shader entry point. So by importing this material module, I can use any public types and functions in that module as if they're defined in the same file. So in this code, I'm using the standard material type, which is defined in that materials module. And one detail here is that you can import a module in its binary form, and the .slang file that implements the module, the materials module, does not even need to exist when you compile this compute module. So what will happen is that when you compile this compute module, the compiler will try to resolve the file for this import declaration. And when it sees that import materials, it will first look for materials.slang module file in all the search paths. And if it is found, then you will just use that binary file directly. And in that case, the compiler will not be parsing or type checking anything in the materials modules because it's already done. And if that binary is not found, you will then proceed to find materials.slang file and try to compile it from source. And another important aspect of modules is that they are cached within a session, like once loaded. Let's say we have a very small engine that comprises 3 modules, the materials module and compute 1 and compute 2 modules that both imports materials. Now let's say we want to compile compute 1 and compute 2 to SPIR-V. And to do that, you will first create a Slang session, and then you load the modules into the session. All right, so know that when you are loading this compute 1 module, Slang will also implicitly load the materials modules into that session because compute 1 imports materials. And when it comes to time to load compute 2, Slang will also make sure that the materials module is loaded because compute 2 also imports materials. And because the materials module is already being loaded as part of compiling compute 1, the compiler won't need to do anything further here. So as you can see, even though the materials module is being referenced twice, it is only compiled and loaded once, and that is how you will save compile time. And to give you a concrete data point on how much modules can save compile time, we created a path tracer comprises 16 modules, and the path tracer will compile into a SPIR-V that is 161 kilobytes in size. To measure the benefit of modules, we made a random change to one line of one of the modules and recompile the entire shader. And with the Slang module cache, such recompile will only take 210 milliseconds. But if I write the entire path tracer with HLSL that everything is just pound included together, you will take DXC 570 milliseconds to do a recompile. So the time savings comes from the fact that any module that is not changed does not need to be recompiled or rechecked. And here's another example that illustrates the benefits of modules. Let's say your game has 5 shaders that is implemented in 5 different files, and each shader will pound include the files that implements the shading features required by that shader. So these files will use different combinations of the same set of features that your engine supports. And with pound includes, there is really no way to reuse any compilation for things like materials and lights across different shader compiles, because they are pasted into the shader file by the preprocessor before any parsing and type checking. So there will be a lot of redundant work to compile these 5 shaders. But if we implement all these features with modules and referencing them with import, then we can skip all the modules that have already been compiled before. So this means that each module in your engine will be compiled at most once, no matter how many shaders are using them. And you may wonder, what does it really mean when I say that compiling a module? And to clarify that, let's look into the compilation process a little bit further. So in a pound include code base, for each shader, we are pasting together a bunch of code, and that code will go through the entire pipeline, including the parsing, type checking, IR generation, IR validation, and optimization, and finally, you get at SPIRV output. And you can see that all this material or lighting code is just going through the entire pipeline twice, despite they're essentially the same, right? Because I have 2 shaders, I have to compile every line of this twice. And with modules, it's a little bit different. So I can run the first half of that compilation pipeline once for each module and produce the Slang IR binaries for each shader feature that the engine has, right? And then for each shader, that is basically a composition of those modules, I just need to link together the needed modules and then do the backend optimization of the link code and then produce SPIRV. So you can see that all that front-end work is being reused across different shader compiles. And that is what I mean by saying the module is compiled once. Is all that front-end type checking, parsing, and some IR generation validation work. And a caveat here is that in order to reuse these precompiled modules, we need to make sure that the preprocessor settings for compiling shader 1 and shader 2 are the same, because the preprocessor setting can affect source that reaches the parser, and the modules compiled under one preprocessor setting will not be able to be reused in a compile that has a different preprocessor setting. And this means that you won't be able to save as much compile time when every shader requires a different preprocessor macro setting. And since you will need to compile every module from scratch under that new preprocessor define. And in the Slang compilation API, this is also obvious. The preprocessor macro defines will need to be set during the creation of a Slang session, and it can't be changed once that session is created. So this means that if your code base is heavily relying on pound defines, then for each unique preprocessor state, you will need to create a fresh session for it. And a session is what caches the loaded modules in order to reuse them between different compiles. And the more unique sessions you need to create, the less you can benefit from module reuse. But the problem is the preprocessor pound define is considered the main way to do shader specialization by most developers. And why can't we? So yeah, the problem is we really cannot just afford the performance cost of not doing specialization. So what can we do? to use modules and benefit from compile time, and also be able to get all the performance benefits, the runtime performance benefits from the shader specializations we do today. And the way ahead is that we would recommend developers to stop relying on the preprocessor for shader specialization. And to make this possible, you will need a couple more Slang features. And if things are done right, you should be able to use a single Slang session for all your shader compiles that will give you the maximum benefit of module reuse. And I will show you how that can be done with a couple examples. So in this first example, we have a shader that implements two types of materials, the simple material and the Disney material. And I have defined the parameters in struct types. And also I provided this shade function that implements each type of a material, right? And then I have a fragment shader that calls into the materials implementation to do the shading. And I want to be able to specialize this fragment shader to different materials. So I introduced this like use simple material macro and use that to control which material type to use in this shader. Now let's see how this example can be done without using preprocessor macros. So the solution here is to use Slang's generics. So here we define an interface iMaterial to define what a material type can provide, which is a shade function. And then we can define our simple material and Disney material types that implements the interface. Note that it both implements the shade function, also it defines the parameters, the shader parameters like the textures required by that material type. And the final step is to make our fragment shader, the fragment shader entry point. We make it turn it into a generic function that is parameterized on this material type. Now you can see there is no longer any use of preprocessors, but how do we specialize this shader to different materials? For that, you will use the compilation API to do that. So we will first load the module into the session, and then we find the entry point from the module, and then we can specialize this entry point differently with different types, and then request target code from that specialized entry point. This way, we only need to parse and type check frag.slang once, because that M object here can be reused over and over for different like specializations of the entry point. And another example here is that comes up very often in a lot of code bases is that for a single material parameter, right? So often they can be sourced either from a texture or from a simple constant. So we want to be able to specialize the shader based on where that parameter comes from. So with the preprocessors, I can define this diffuse source macro so that when it is defined to 0, we will read from the constant value. And if it is 1, we will declare and fetch from a texture. Again, this can be achieved without using preprocessors. So I can define this iChannel interface that represents a parameter, which declares that any implementation of a channel needs to provide a getValue method that returns a parameter value at a given UV coordinate. And then this iChannel interface is implemented by two types, the const channel that represents a constant value, and texture channel that represents a texture. And with this, I can change my simple material type into a generic struct itself that is parameterized on the channel type for diffuse and specular. And I don't need to change anything about my fragment shader entry point, because with this, I just need to specialize the same entry point with different specializations of this simple material type, right? So let's look into one more case here. So here, we want to specialize our shader to different set of vertex interpolants. So the context here is that some platforms are performance sensitive to the number of vertex interpolants that get passed between vertex and fragment stages. So we want our shader code to define only the vertex output that are actually in use. And this is normally achieved by defining things like has normal, has tangent, and has color macros that guards the definition of the corresponding struct fields. And if I do not define has normal, my vertex out type will not have that normal field. In Slang, this kind of conditional fields can be defined with the conditional type. So here, instead of using preprocessor macros, we simply turn our vertex out type into a generic type parameterized on has normal, has tangent, and has color. And the normal field here is defined with the conditional type, so that when has normal is set to false, that field will get specialized out and removed from the final target code. And with that, we can turn our vertex and fragment shader entry points into generic functions as well, and passing that has normal, has tangent, and has color setting down to the vertex out type. And we can then specialize these entry points to our needs using the same compilation API calls like we did with the previous materials example. And one major downside of this code, if you have already noticed, is that there is a lot of boilerplate defining and forwarding the has normal, has tangent, and has color settings. And this is making the code looking very busy for the simple thing we want to achieve. So the next question is, can we still get all the benefits of this module compilation without having to write all this boilerplate? And that is the major motivation for the next Slang feature that I'm going to talk about. And these are link time constants and types. And this feature enables Slang specialization without requiring a lot of generic boilerplate. And here's the same shader written using link time constants. So here, the external static const declarations declares that the shader needs these three constants provided at link time in order to produce the final target code. And the link time constants can be used in type signatures that defines the normal, tangent, and color fields as if they're like any other compile time constants. Notice how much simpler the shader has become, and there are no longer any generics or angle bracket syntax in this code. And the nice thing about this is that you can compile this code directly into a Slang module without providing the concrete values for these link time constants. And you can then specialize this precompiled module by linking it with a separate module that defines the values for these constants. So here, I create a separate module called config that defines the values of these constants with export static const declarations. To specialize the shaders.slang module, we will first load it into a session, and we will also load the config.slang into the session. And after that, we link the two modules together as a single program that using that create composite component type API call. And then I can produce the target code from the linked program, and the target code will be specialized with the constants. As you can see, I can specialize shaders.slang differently by linking it with different config.slang files. And no matter how many times I need to specialize it, the main body of that shader.slang file is parsed and type checked once, and only the smaller config.slang needs to be checked for each specialization. All right, so in addition to link time constants, Slang also supports link time types. And recall our first example where we are specializing the shader to different materials. I said earlier that we can get rid of preprocessor usage by making the fragment shader entry point a generic function. But you don't have to do that. You don't have to write a generic function if you don't like the generic syntax. And here's a different way to specialize that shader using link time types. We will define this iMaterial interface and implement it as usual. The difference is that now we're declaring a link time type called material that conforms to the iMaterial interface. What is highlighted lines is saying is that it declares that there will be a type called material that is provided at link time, and that type conforms to the iMaterial interface. The equals simple material clause is simply saying if there are not any other modules that define what material is, then it will default to be the simple material. And then the rest of code just uses material as if it is a concrete type. Again, we can compile this code to a Slang module without knowing what material is. And similar to link time constants, we can specify the concrete type in a separate module using the export struct syntax here. And in this example, we're specializing this shader to use a Disney material. And finally, I strongly recommend checking out this end-to-end example in C++ that demonstrates how to use Slang's compilation and reflection API to work with link time constants and types for shader specialization. All right, so that is all I want to cover today. So as a quick recap, we started with a syntax for defining and using Slang modules. And we talked about how you can define modules in multiple files. We also talked about why modules can help speed up compilation due to the ability to reuse compiled modules no matter how many times they are being imported. And we also discussed why preprocessor macros breaks the compile time benefit of modules. And when we continue to talk about all the Slang features that you can use to do shader specialization without using preprocessors, so that you can get the maximum benefit from using modules. And the features that you will use instead of preprocessors are generics interfaces, the conditional t-type, and also link time constants and types. And I hope this is like enough information to get you excited about trying out modules in your projects. And finally, before I wrap up, I like to just remind people that recently we did this. We have presented a SIGGRAPH course that is about how you can use neural shading and how you can do like neural shading and inferencing training MLPs with Slang. And the course materials is already available at this link, and we are still working to get a recording of the entire course available, and we will make that available pretty soon. And then in SIGGRAPH this year, we also have a Birds of Feather session just on Slang, and the slides and recording are also available on the link. So highly recommended that you check them out. And also as a forecast, like so I think for our groundback sessions, like we have decided that the next session will be we'll be talking about automatic differentiation, and the scheduled time will be sometime around October. So if you're interested in that part of the language, please stay tuned. All right, so with that, I will turn to some questions. I do have some bonus content after all the questions if we still have time, but I would like to make sure I address people's questions first.
Excellent. Thanks, Yong. The first question I have is from Adi Barlev. He asks, what happens when a deep header file shared by many modules is changed? Is the compiler aware that modules and shader above need to be compiled? And is there any optimization done for this process?
So if you are, okay, so I guess the question is more like, if module A imports module B and module B imports module C, and sometimes some people make a change in module C, and what will happen, right? So it's usually if you made a change, so if you made a change to module C, and if that affects and that change affects the public signature. So obviously that is going to, if you're changing the signature of a public method, then definitely that's going to result a cascaded recompile of module B and module A that uses them like as soon as the change is visible from the public, you're changing the public boundary. But if you're just changing the implementation, then the module B and module A will not need to be changed, or will not need to be recompiled.
Great. Another question is, are there any plans for REST API to Slang compiler?
Sorry, what's that? Can you repeat that question?
Are there any plans for a REST API to Slang compiler?
REST API. So that we have not planned for that yet. But things like that can be done as a wrapper on top of the existing API. But then you will need to handle like all this serialization, deserialization, and like all this RPC related work on top of that. So for the core Slang compiler API, we're not really thinking about that right now. But if anyone in the community feels excited for those, yeah, we definitely will welcome contributions to make that possible.
Okay. Next one. Is there an easy way to link and specialize with Slang C instead of a session?
So for complex compilations like this, we do recommend using the compilation API instead of Slang C. But if you are wanting to use Slang C to do this linking, it is possible. So Slang C has, if I remember correctly, has this experimental feature where you can put multiple .slang module file as the input file to Slang C, and Slang C will do linking and code generation from that. However, that feature is not being as extensively tested as the compilation API. So if you run into any issues, please make sure to report them, and we will make sure to fix that. It's just that we envision more people like engines will be using and approaching Slang compiler via the API. So the Slang C support for this may not be as stable in comparison.
Do I need to manage modules by hand to have some kind of incremental compilation? It says, my pipeline is next. Several modules get compiled by Slang C into a single output file with compute core. Does the compiler have any kind of cache?
So if you look at our compilation API, we actually has the ability for the compiler to automatically detect if a existing .slang module file is out of date. So basically, what happens is that in each .slang module file, we store a hash of all the source files that are used to compose that module, and also all the compiler options used to compile that module, and also the Slang compiler version that is used to compile the module. And whenever you are loading a module and you tell Slang to verify its up-to-dateness, the Slang compiler will then recompute the hash given all your inputs, or your input files and configurations, compiler option settings, and all that, and compare it against the hash in your existing file. And if that hash does not match, the compiler will recompile your code from source if source is available. So that does exist, and there is also a dedicated API that tells you if a module is up to date. So there are some help inside the compiler that helps you using like a pre-compiled checking and using a pre-compiled module. And in fact, that if you dig into the Slang Pi code that we have, it is heavily using all that features to aggressively cache and reuse pre-compiled modules. So if you write a Slang Pi program and you change one file, it's just that very minimum amount of code will get recompiled Yeah, so that's the support right now. And also
Yes.
the compiler also, I believe, has the Slang tool also has a option to export a set of dependent file similar to other C++ compilers, and that dependency file can be picked up by a build system to automatically detect when to trigger a rebuild. So all that basic level support is there.
Excellent. Do integration with build systems like CMake/Ninja exist?
Um, that we don't particularly, we have no particular support for any build systems. So what we provide today that can be invoked by any build system is just a Slang tool. But it should just work with at least with CMake, it should just work if you write your CMake file, express your compilation as a tool invocation. But we have not exposed Slang C compiler as a tool chain or something like equivalent to that concept in any build systems. So there are no like specific support for that, but some of our users are finding a successful way to integrate it with CMake just fine. But again, this is an area that we could be improving, but it's not being prioritized right now by the core team, but we always welcome contributions to make this better.
Excellent. I have one last question. Does Slang's generics work the same way as C++ templates? Are there any additional runtime overhead associated with generics?
Yeah, so runtime overhead, no. So generics, when they are specialized, they will produce the exactly the code that you would expect, as if that thing is getting the type or value is getting substituted in code, and there will be no additional overhead in abstraction when you use generics, especially if you specialize it with a concrete type. And as for like the differences with C++ templates, actually this is a question that I got asked a lot, so that I even like prepared some slides for this. So maybe we could use, if there are no other questions, I guess I can use the rest of time on this. But before that, I want to make sure there are no other questions.
No, yeah, you're good to go.
All right, so let's get into that. So I think this is actually aligns very well with a little bit of bonus content that I prepared for this talk. So let's get into those slides. So yeah, you asked a question about generics and templates, and are they different? So this is something that I always wanted to find an opportunity. So now that there's a question, I think this would be a very good opportunity for me to explain the differences between generics and templates and why Slang chooses to support generics rather than like templates, which is more familiar to most graphics programmers that uses C++ in their day jobs. And in case you're not familiar with the differences between generics and templates, the key distinction here is that generics are being checked and compiled to IR before they are specialized. So here I'm showing this code that will serve as an example that could make this point very clear. So here we have two overloads of the foo function, one that takes an int and one that takes a generic t. And then I also have the bar function that calls foo. So now the question is, which overload of foo is bar calling? Okay, so if this is C++, if this is templates, then the answer is it depends, right? So if you specialize bar with int, like in this example, then you will be calling the first overload. But if you specialize it with something else, you will be second overload. However, in generics, in Slang, we will fully type check the definition of bar without specializing it first. And this means that a compiler will select an overload of foo before it knows what t is. And since there is no non-conversions from t to int, the compiler will simply pick the second overload of foo. And once that overload is resolved, we will compile this generic function into IR. And the actual specialization of the bar function happens during IR optimization. So when that is way after the overload resolution is done. So all the specializations of bar will be calling to the second overload of foo, no matter what t you plug it in. So that is the main distinction, is that with generics, we are able to type check early without looking at the specializations, and then we are able to convert it to IR without looking at the specializations, and all the specializations would actually happen at IR level instead of AST level, right? So that's the difference. And so just to restate what I just said, so generics fully checked, compiled to IR without being specialized, and specialization done in IR, right? So not in AST before any parsing or checking. And this is what this means is that if a generic function is parsing type check, and all the call size of the generics also parsing type check, then that together will guarantee the specialization of the generic will result in a valid code during the IR optimization stage. And we can compare generics and templates from different angles and discuss their pros and cons. So for example, for modularity, I think generics is a win because it allows the generic function body to be fully hidden from the use side. And because we can compile the generic function to the IR directly and specialize it in the backend, right? So when the compiler checks the call of a generic function, it only needs to know the signature of that generic callee, and it does not need to know the body of that function. So this is in contrast with templates, where the body of the template function needs to be made visible to the use side, because they need to be expanded to the use side in order to complete the type checking. And that will break the modular boundary, because you are not able to hide or detail for compilation, right? And then for compile performance, this is another win for generics, because the compiler can parse and type check and then generate code from a generic function body all by itself without looking at all the specializations, right? And then each unique specialization, like if you have templates, then that template needs to be expanded for each call side, and each unique specialization of that template will need to be type checked independently. And also this has a effect on diagnostic messages. For example, in generics will give you usually will allow the compiler to produce cleaner messages that will pinpoint a problem, but templates usually will lead to a long stack of messages that are often difficult to parse. And for code generation, technically, generics is also more flexible, because we can technically lower a generic function to dynamic dispatch, even though we don't do that today, but that's something possible on the horizon. And if we do that, we can just generate code that uses dynamic dispatch instead of specializing and create a bloated structure. If future GPUs are, for example, made that runs more efficiently on unspecialized code, then you don't need to change your code. You just need to compile that generics differently. Versus templates, it's basically requires you to buy into this static specialization, and there's no way you can compile a template function into something that uses dynamic dispatch. And finally, the one downside, I think, with generics is that it's less powerful than the full C++ templates, because you can do very complex metaprogramming with templates. Although in many cases, those powerful metaprogramming will result in code that may be a little bit difficult to understand or maintain. The thing is that we think there won't be as much a great need for the scenarios where Slang cares about. So we think that generics with a powerful type system is often sufficient, and especially for the benefits it offers. So yeah, in one sentence, generics works well with modules, but templates don't do as well. All right, and this links back to the high-level philosophy of the Slang project that I want to highlight here is that we want to design a language that will not solve today's problems, but also ready for tomorrow's GPU programs. And since the start of the project, we envision that modular development will become more important as GPU code are getting increasingly more complicated. And we also envision that future GPU architectures will have better support for true dynamic linking and function pointers, which will allow us to eventually separately compile different modules down to native GPU instructions and completely solve that shader combinatorics problem. And for this reason, we want to make modules and separate compilation the first order consideration of the language design. So the choice to support generics rather than templates is not because we don't like C++. In fact, we are both fans of C++. We use C++ to build Slang, but rather we want our language to have a better path of scaling into the future. And so, yeah, that concludes that's a long answer to that question. So, yeah.
Yeah, it was great. Pablo followed up with any plans for template support as well for module local metaprogramming?
So yeah, that's a really good question. So in theory, technically, like there's nothing preventing a language to have both templates and generics, and especially for people wanting to do template-like programming. So technically, that's definitely possible. It's just that to implement templates, that requires a lot of effort. So, and for the additional benefit you get from template, is not something that we see worth the time investment of the core team. But yeah, from the technical point of view, there's nothing that these two technologies can't coexist. But a lot of what template can achieve, you can achieve it with generics. So there's already a lot of overlap in terms of functionality there. So now that Slang has already supported generics, adding templates back to it feels like a lot of redundant work on to achieve the same set of goals. And also, like generic templates will always have the problem to work across different module boundaries. So carefully implemented to the right way is also difficult. And the other thing about adding templates here is that it has the risk of creating more confusion among the users, like when to use templates, when to use generics. And unless you are super familiar, maybe most users who will just use templates and then lose all the benefit of modules. So overall, we think that it's possible to do, but it's not something that has a lot of value. So it's probably not something we will be doing anytime soon.
Excellent. Excellent. Thank you, Yong, for teaching us about Slang modularization. We appreciate your time and effort in putting this together. As a reminder, a recording of this presentation along with the slides will be available on the Slang website, and a direct link will be sent to you in a follow-up email. As you leave the webinar, please take a moment to fill out the survey that pops up. Your feedback is important to help us improve these presentations, and please let us know if there are any other Cronus-related topics you may be interested in. And thank you for joining us. Have a great day.